everybody and welcome to another video. Today we are gonna combine the concepts that we learned and explored in the videos C++ static storage implementation as well as C++ initializer list overview and implementation. All of that in order to pull off this kind of structure, inline structure of our static storage in order to fully re-implement the initializer list that is implemented, that was originally implemented at the compiler level in C++ 11. So I will be walking you through all of the handicaps and limitations we are gonna face with this, since initializer list is almost impossible to re-implement, since we don't have control over the compiler. And that's how C++ 11 standard integrates the initializer list. So not only is it a class behind the scenes, but also the compiler makes sure to generate the most efficient code for that. And what I mean by efficient code is a scenario where, and we talked about this plenty in the C++ static storage implementation and initializer list overview and implementation, and that is the unnecessary move semantics and possible copy semantics that are taking place or that take place between or before we even place our entities into that data buffer. And also we also talked about initializer list copy and move semantics, and we really dived into the ins and outs of it. So make sure to check out before the two videos before even trying to brush up on this one. All right. So the idea was that if we re-implement static storage and we do pushes like this, or we add something to our static storage, we will end up with this code here. If we look to the right now, to the right split screen, we'll see that we create the first S, we have to move it, we are enforced to move it, and then we call the struct, or the code rather invokes the destructor, since the R value lifetime ends at the end of that expression, which is marked by the semicolon. And I also like to note that semicolon is used to represent the end of an expression. And when I read the code, I use that criteria in order to figure out where does the expression actually end. But in languages where we don't have semicolon, it can be tough to figure out. Or rather, when in languages where the semicolon is not required. But that's neither here nor there. What we're seeing here is the unnecessary move, the unnecessary destruct. And in order to remove that or eliminate those overheads and create cleaner and generate cleaner and have more efficient code at runtime, we defined a macro that will take the storage and will apply the new placement on the static storage. And we also made sure that all the elements within the static storage are public, or in other words, we can treat it as a struct even in C++, since structs have all the members public to it. And when you have, and I have really no problem in defining all my members public if the ultimate goal is to have the most efficient code at runtime. All the compile time checks sometimes pale in comparison to how crucial the performance is at runtime, since that's when we actually get to run our program but not compile it. So this now makes stuff really difficult and makes life really difficult in order to replicate the inline constructor that the typical initializer list has. And I've tried many approaches to pull this off. The first one is to create a template print that takes in multiple arguments, and I believe this is available from C++ 11 on. But however, the problem with that call, or if we place this in the constructor of the static storage in order to pull off the inline constructor of the initializer list, I mean, that's how I refer to it anyway. There's probably a better term for it. I can't remember right now off the top of my head. It is, one second, I think it's assignment constructor. Oh no, it's not. Let me try to look for that term. Well, you can say static initializer, it turns out. But yeah, if you want to pull off the static initializer, this is definitely not going to cut it, since once we get to the point of the function where we need to execute something like storage add, and it would be my buffer within the class, actually would be T now. So if I do this, I will have to enforce the move, since at this point it is move, it is R value, but if I reference it, it becomes an L value. That's why in a lot of C++ code, I mean all the C++ code, you will see where we take the R value on the inbound of the function, but once we actually get to use it in the function, we will have to enforce the move. And that way we are invoking the move constructor of our underlining type of the storage, which means we will end up in the same scenario that we ended up right here. And that is not what we wanted to do, and this approach really gets thrown out of the window altogether, since we cannot really have the inline static initializer that we would have with the initializer list. And that is also the case because the compiler at compile time makes the necessary transformations, and turns our initializer list into something like this behind the scenes. But visually, when we are writing the code, we cannot see that. So there is additional work that is done behind the scenes to provide or to feature such functionality. But what's really interesting about, and I would like to point that out in this video, is once you have this sort of variadic arguments, template arguments in C++, you would think, okay, this looks like a recursion. It looks like a recursion, but at runtime it's not. If we reveal the linked code, you'll see that we are generating the print SSS for 3 S's, for 3 arguments rather, and then for 2 arguments, and then for 1 argument. But if I put in the 4th argument, the compiler will generate the one with 4 template arguments. And we can also, and one other thing, so to prove this is not a recursion, is that we can actually inline all of this. So if I look for the print, and if I apply the O1 optimizations, which should have all my functions inline, there is no such function reference whatsoever. So we are indeed able to inline such template function with variadic arguments in C++. So definitely this is not a recursion. And what I also find a little bit confusing from the C side of things is that this right here, print, once you define a template function where you have the R value reference, this will also work for the L values. So if I refer to my struct S as an L value here, it will compile and it will work just fine. And that is because that's the magic of the template, where your argument is the R value reference. It's a trick, I agree. It doesn't make much sense because you would expect it to be something like this. But in the modern C++, you cannot enforce the forward on a const reference. So people, or actually the C++ community came up with this approach where automatically my template function will substitute the required reference types once I call the function, or I refer to it like this. So yeah, that would be it as far as the multi-type variadic macros. So there is one more approach standing on its last legs, and you will see in a moment and you will see it in a moment, where we have a static storage, and now in order to have such static initializer, we are defining a variadic macro. make sure to check out this Wikipedia page to get yourself up to speed with what it is. But I will explain the, I would say, the crux of it in a way, so that why can this be confusing? If you look at this get macro, look at it as a getter where it returns the another macro at compile time. So what this variadic kind of macro does is that allows us to generate, and I will include the E flag so that we can see the output at the preprocessor level, since that's where the replacement magic happens when we are using macros in general. So you will see that we are generating three pushbacks onto our static storage, and that is because the compiler keeps generating, that's why it's named for each, it keeps generating the sort of unrolled version of the for loop at compile time, so that we can pull off something. But what we are actually essentially doing is that we are pulling off something we've done previously in the video, and that is when we are applying storage add macro on each pushback of the storage. But here we are actually generating that code without repeating each line. Now this approach can be probably preferable, since we can just take, if you're using Vim or Emacs, we can just take that line and we'll say this, we'll go with that, and we'll change what we need to put it or append to that storage, and I will change the static size t of it, and voila, that would be all. But if you really want to have one macro reference, you would need to generate your code via variadic macro. And I thought about this, and it came to my mind, since there was once upon a time I did solve this kata at Code Wars, where we are micromanaging our code in order to create tuples that can be, or macro, or tuples or string concentrations that depend really on the macro. It can take 1 argument, 2 arguments, or 3 arguments. So in order to have these arguments, these are arguments optional, you will need to create FE1, FE2, FE3, and the get macro getter will get the respective one in such a way that, see this one here, you say VA arguments. First, we're passing on the storage and the type, because that's the necessary parts of our macro. And then this is really interesting. If at compile time or at preprocessor level this gets replaced and becomes get macro storage t and becomes 1, let's say, or S1 actually, and then becomes FE1, FE2, and FE3, actually 1. And if you track down this macro, you will see that it's now storage type. 1 becomes S1, FE becomes 2, FE2 becomes 3, and we get the name which is for 1 macro argument. If we put in 2, at the preprocessor level, we are gonna get to FE2 since S1, S2, F3, and now F2. If we are getting our macro for 3 macro variadic arguments, now it is S1, S2, S3, and F3 we're getting. So we are always gonna hit the nail on the head and get what we want to get. So that's how it works behind the scenes and or under the microscope. And as I was looking at this macro, I was a little bit perplexed by it. But as I moved on and try to think about it long and hard, it's essentially just you get your macro, you need to pass on your arguments accordingly. I was brute forcing at the beginning, but in the end I got it right once you sort of grasp the concept of. Now the most difficult part for me was what is M here? Well, the M is the action, right? And then I'm passing on the storage, and then T, and then the item in this case will be the VA arguments, and that will be X for me. And once I am referencing M, I'm actually referencing storage add, and it's simple as that. And once I replace the storage add with storage T and item, storage T and item, that's it. So that's how it's going to work behind the scenes, and that's how we accomplish this. So let me just run this code so that we can wrap up this video. Now we are getting the output, the desired output we were looking for, and that is as clean as it gets. And now if we compare that output with the initializer list output, it's the same behavior. Yeah, let me just do that. It's the same behavior, and that is we are not forcing any redundant or unnecessary moves, and destructors, we are just getting straight to business, and that's the optimization to make when it comes to this kind of stuff. Now this is definitely a limitation of a macro when it comes to its implementation. So it's limited because if I put in the fourth S in here, that is gonna break. In order for me to fix that, I'll have to add another FE4 that will call the FE3. So if I do something like this, it will be 3, and then I will need to get a 4 here, and then I will need to get a FE4, and I think that should work. Let's see. Free invalid pointer. 1 second. Let me just break this down over here, and on Valgrind level, main invalid, free, realoc, F2, F3. I thought I had this, but apparently not. How about, no. F4, we're calling F3. I'll see what this issue is, but since there's not enough time for me in this video, I don't want to make this video like 2 hours long. It depends on the action, depends on the storage, depends on the T. Oh, this should be 4. Oh my god. Okay, okay, and that's pretty much it. Let me just check that by Valgrind. That should be 4. Now this is the also the problem that initializer list solves very efficiently, because it's generated at compile time, is that it takes the size of the static initializer list and just does this 3. So if I change anything in here, the compiler will automatically change it to 4. But for my static storage, that is not the case. And we can improve the static storage macro to do something like that, but it becomes really tough to use then. But yeah, that would be all for this video. Thanks so much for watching, and until next time.